You can unmute and turn your video on. So Ian, it was great to meet him last night in the networking session. He's chief engineer, director and chief engineer at International Electric Company, which does a lot of focus on wireless power transfer. And I think he's going to tell us about Cassiopeia, this orbital phased array. So I'm very interested to hear about it.
Okay, first of all, can you see my screen okay and hear me?
Yeah, you look good, sound good.
That's great. Well, thank you.
See your screen, Ian.
That's great. Thank you very much for the opportunity to talk. Thanks for the introduction. I'm a director of International Electric, and we are part of the UK Space Energy Initiative.
Ian?
Our main focus. Hello?
Are you going to be sharing your screen?
I thought I was.
Oh no, I'm seeing your screen. I'm seeing you, not your screen.
Okay.
Share screen at the bottom.
Sorry.
There we go. And now I see your PowerPoint slides. That looks good. I see a little, yep, and then we see the right screen.
Okay. So our main focus is on utility scale power beaming to Earth. But we do recognize that there's probably an opportunity to, there's probably more chance to have power beaming on the moon before we ever have a chance to beam significant power to the Earth. So I'm the inventor of the Cassiopeia solar power satellite, and it has, for the Earth beaming version, it has a specific power in the region of about 1 kilowatt per kilogram, so much higher than many other concepts which have been proposed. And that's by virtue of its design. So it's constant aperture, which means we have an omnidirectional steering envelope, electronic steering. Solid state, there's no moving parts once it's deployed, and there's no electromechanical systems needed to achieve its primary functions. It's integrated, so all the primary functions are, you could represent in a 6mm cube at 24 gigahertz. And orbits include, obviously, lunar orbits, surface power beaming, and particularly highly elliptical orbits, which have some benefit for Earth. And this is a unique phased array, and the capability of this 360-degree power beaming is mainly down to the constant aperture provided by a helical geometry. Now, we've seen slides very much like this yesterday and today, but I'd like to just dwell on it for a moment to consider where are these instruments situated which have observed the lunar poles, and quite obviously they are in lunar polar orbit. And that strikes me as probably a very good place to put a power beaming asset in order to give you access to all of the craters rather than landing a power beaming asset and then your choice is limited to one or two. So just to get back to the basics of low and high gain antennas, low gain antenna, you don't need to steer it. It's got omnidirectional field pattern. The only place you can't receive or transmit is along the axis of the antenna, but it's too inefficient to even consider for wireless power transfer. High gain antenna, the beaming range is determined according to the size of the aperture and the wavelength that you choose. But it needs mechanical pointing to cover more than about a 90 degrees azimuth. And this is where Cassiopeia gives you the best of both, because it's a high gain antenna, but it has a steering envelope which is equivalent to the omnidirectional antenna. So basically no steering is required as long as you're not trying to point the axis at the receiving target. Very low mass, I mentioned we can achieve a kilogram per kilowatt, but that's at 2.45 gigahertz. And what I'll be showing you following this is based more at 24 gigahertz, moving to a higher frequency, which wouldn't be suitable getting through Earth's atmosphere, but could be very suitable for delivering power to the moon. So first question, obviously we've got trade-offs, and a major one which has been discussed yesterday and today is should we be going laser or microwave? And obviously both systems have their benefits. So laser power transfer, as we're all aware now, has much smaller apertures, potential for longer distance beaming, but it does have some challenges as well of coping in the presence of levitating lunar dust and having mechanical pointing where that lunar dust is very abrasive and could damage optical surfaces. For Cassiopeia microwave power transfer, yes, you need larger apertures. The ranges aren't going to be as great as for a laser system. But what I've shown here is just one example to power something equivalent to a Curiosity type rover. So it's by no means the limit of what could be achieved on surface-to-surface power beaming. But this example shows you for 2 kilowatts of RF at 24 gigahertz, you can beam over a kilometer. And for a 1 meter rectenna, spherical rectenna is shown here, you'd achieve about 200 watts of electrical power and 130 watts of heat, which could be used to keep the electronics warm. So that's, like I say, it's not the limit of what could be achieved by a long shot, but it is one point in the sand which could power a Curiosity style rover. But I'd like to move beyond rovers and look at the power requirements for a lunar settlement. So we currently have one example of long-term human habitation in space, and this might be slightly outdated now because the ISS has just received new rollout solar panels, so the power capability is probably increased. But at the time that this study was done, it was a little under 50 kilowatts of electrical averaged over the orbit that was delivered. In comparison, I've used as a separate reference point the International Space University, their Lunar Gaia study, and they came to the conclusion that you'd actually need about 650 kilowatts of electrical baseload power to sustain a long-term habitation on the moon. So that unit of 650 kilowatts is what I'm using from now on to compare different systems for power to the moon, principally comparing microwave power beaming with surface photovoltaics and nuclear options. So many will have also seen this excellent graphic which showing the conditions you could expect at lunar pole. And this is showing obviously a photovoltaic system. And key points to achieve 650 kilowatts of baseload power. This is assuming that you're in a region which has a high proportion of sunlight, maybe 80% of the lunar month. But you're still going to need a great deal of energy storage. It would be ridiculous to even consider lithium-ion battery storage. You'd end up with something about 5 times the size of the large Tesla Hornsdale Power Reserve in Australia. But for using LOX and LH2 storage, then you're going to need something like 33 tons for this 20% of night that you're going to experience. And you can see in this image that you can see instances where the PV is shadowing itself. You've got a lot of terrain shadowing. You're going to need to raise your PV up high and have it rotating on a vertical axis to track the sun as it travels around the horizon. Another option is nuclear power on the moon. This is the NASA kilopower fission reactor. And this design goes up to about 10 kilowatts. I understand now that there are other proposals as well which may achieve better specific power. But based on this, to achieve 650 kilowatts, that would be 65 soft landed units, which is about 100 tons soft landed on the moon. But of course, you don't get a soft landing for free, and that's equivalent to about 500 tons in lunar orbit. So I think that's the measure which should be used to compare is how much mass needs to be taken to lunar orbit before soft landing. And I think there's a benefit to leaving your power beaming asset in lunar orbit rather than trying to soft land a surface-to-surface power beaming system. So this is an example for a polar orbiting Cassiopeia solar power satellite. And this, if you like, is a minimum system which could achieve 650 kilowatts of baseload power. So starting with just 2 satellites in an offset orbit, the orbit is just shy of 150 minutes. So with the 2 satellites, you can have just under an hour between 20-minute bursts of power received. So you are going to need some storage, but not a great deal, certainly not anything compared to the 14 days of a long lunar night, or less than that in a specific polar region. There are no stable sun-synchronous lunar polar orbits. So a point I just want to make here is that if you are in a polar orbit, you may start in a dawn to dusk orbit, where looking at this, looking at the moon here, you are actually the sun. But that's going to migrate to a noon to midnight orbit over time. And shown here is the case halfway between that and 2 different designs of solar power satellite, one of which is using rotating PV, single axis of rotation, and using gravity gradient stabilization to keep its microwave transmitter pointing at the center of the moon. And this is just showing you that for 45 degrees of circular orbit, you would have to rotate the satellite so that it only has rotated by 35 degrees to maintain center of mass pointing. And obviously that's going to be very problematic without massive momentum wheels or control moment gyros. And you would need 2 degrees of freedom on your photovoltaics. You cannot do this with 1 degree of freedom. In contrast, Cassiopeia always maintains a sun-facing attitude. So it can quite happily beam to any point on the moon and doesn't need to maintain any gravity gradient stabilization. This also means that it would be happy in slightly or even highly elliptical orbits, which again, many other solar power satellite designs may struggle with. So moving on, this is an example of equatorial power beaming. So in here, you're going to a slightly higher orbit, 2,600 kilometers. And again, for a minimum solution, you could have 2 satellites able to deliver the 650 kilowatts at local midnight for the whole 14 days of night on the moon. During daylight, you get nearly triple that amount of baseload power available. And these 2 off satellites can serve multiple sites around the moon. So you don't have to consider new power sources. You've got some redundancy by starting with 2 satellites if one should fail. But then that can be extended to give you power beaming to other habitats around the moon. And by extending to 7 satellites, then you can have continuous power beaming, baseload power with very minimal storage. And that would be up to an average of 12 megawatts to each location. And this continuous power beaming from an equatorial orbit extends quite far north and south, about 45 degrees latitudes, plus the small amount of obliquity. So going out much further still to Lagrange point 1 or 2 with the moon, then this is when you're getting to serious amounts of power, which you could start powering villages and even cities on the moon. Mass here is shown as 660 tons, much less than you would need for utility scale power beaming to the Earth. But here you're getting 180 megawatts of continuous power. And again, this could be extended. And that would be sufficient to keep about 1,700 population happy through the long lunar night. And obviously, you wouldn't just have one asset. You would add further solar power satellites for redundancy and near unlimited expansion across the lunar near and far sides. So in summary, surface-to-surface power beaming benefits from Cassiopeia solid-state architecture. You've got this omnidirectional steering capability. Lunar habitats require reliable baseload power. So if you're considering PV-only solutions, the amount of hydrolox you need is excessive, and it's simply prohibitive if you're looking at lithium-ion battery storage. Satellite power beaming to the lunar surface requires far less mass than nuclear because you haven't got this payload fraction that you're trying to soft land. And obviously the orbits that the assets that you put in orbit can then serve these multiple locations without having to soft land further nuclear power sources. And the storage requirement is minimal compared to PV. Basically, you just need to cover the lunar eclipse period, which is slightly less than 5 hours, worst case. 7 Cassiopeia satellites can deliver continuous baseload power from both polar and equatorial orbits, and that can beam power far beyond just the 80 degrees latitudes, north and south. It can basically cover the whole moon. And all the figures I've presented here, they're based on a paper I wrote, which I have shared with Andrea. So anyone who would like to receive a copy, then just ask, and that will be emailed to you. So thank you very much.
Thank you, Ian. And I would direct the questions to go to the Q&A, and we can do those as other speakers are going on. We're starting to slip some in time, but that's generally going to be okay because we have some time that we can carve out from the breakout session a little bit later today. But I do want to give people a chance to take a break before the panel as well. So